welcome everybody to this follow-up session on metadata systems for end-to-end data and machine learning platforms. My name is Alejandro Saucedo, and just as a reminder, today you will be able to find the link to the slides in the corner over here, so bit.ly/metaup. So you'll be able to access not just the slides, but also the resources that are provided throughout. A little bit about myself. So I am engineering director at Ceylon Technologies, a company focused on providing products, developing products for deployment and monitoring of machine learning models. So we have one of the most popular frameworks for machine learning deployment. I'm also chief scientist at the Institute for Ethical AI, which is a research center focused on developing and contributing to frameworks for the responsible operation, design, development of machine learning systems. And I'm also a governing council member at large at the ACM. So today we're going to be delving into the topic of metadata. And you will be able to come out of this session with some idea of why metadata is so important, even as machine learning practitioners, especially when dealing with machine learning systems at scale or with growing number of machine learning models that you have to deal with. So we're going to be first covering some of the motivations and challenges of metadata in the context of data science and machine learning. We're going to be talking about how metadata is actually different when it comes to machine learning models as opposed to just data itself, the more traditional use of metadata, I guess. And we're going to delve into some solutions that we have quite excitedly been involved in to tackle some of these challenges. Namely, we're going to be covering the Open Inference Protocol as well as the Open Inference Schema. And finally, we're going to be giving a call to action for practitioners to be able to get involved with tackling some of these challenges in metadata. So let's first talk about how it started, right? How machine learning started, when it was kind of like just a bunch of tools back in the day where, when you were going to actually train a machine learning model, it was about choosing a couple of different toolings for your stack. But now if we see how it's going, we have now a collage of ever-growing tools that are set up to be the best for X particular specific area, right? And even more confusing is that we're now converging into acknowledging that there is a need to adopt the best of breed tooling for different stages of the machine learning lifecycle, right? So we have now a challenge of a large number of tools that are available at our disposal with potentially growing questions of how to actually navigate this ecosystem, and more importantly, how to make sure that we can still be not just sane, but ensure that we are operating and managing our machine learning systems and our machine learning models in ways that are robust, scalable, reliable, secure, and responsible, right? So we are now seeing, as I mentioned briefly, a convergence into what is being referred to as the canonical stack. And what the canonical stack basically implies, it basically says that with this large number of machine learning tooling, the consensus is not that organizations will just adopt a single platform that is end-to-end, but instead organizations will adopt a best-of-breed subset of tools for each of the different areas in their machine learning, and potentially even different tools for different groups, right? So perhaps data science for marketing would be different than for pricing, than for operations, than for sales, than for different types of departments within an organization. And this is a very interesting tool that allows you to visualize this. So for the different stages of the machine learning lifecycle, experiment tracking, experimentation, runtime engines, code versioning, deployment, model registry, what are the tools that maybe I could like pick and choose and then see how this would then interact across my entire area. Now, whenever we actually deal with the end-to-end life cycle of a machine learning model, we are dealing with different stages where, of course, if you are a small data science team, perhaps it is the same individual that is performing all of these different stages. However, when you have a large organization with multiple different business units and perhaps a very large data science organization that interfaces with different groups, you are performing handovers of resources at each stage or at each sub-stage of the machine learning lifecycle. So throughout the data operations, the experimentation, the productionization, the monitoring, the operation, and the use case specific processes, there is a element of resources and in this case, metadata that is being handed over from one part to another. So there's a lot of considerations to take into account. Now, we're also seeing that there is a move from what before used to be referred to as the silver bullet of organizational data complexity, which was basically referenced through the concept of a data lake, a central data lake. And there was this dream that organizations were going to be able to adopt a central data lake and perform all of their operations within that central data lake, manage all of their machine learning life cycles, all of their data life cycles within that central data lake. However, what organizations realized and what organizations came into challenges is that centralization then becomes not just a bottleneck, but a challenge because different domains may require different specializations, different tooling, different data products in order to function in an efficient way. And that's why now it's moving into what is now referred to as a data mesh architecture. So it's still true that it absolutely makes sense to have that concept of a data lake, but in the sense of just a lake of data where you have all your raw data. But once you start moving into your bronze data sets, your silver data sets, your golden data sets, where you're actually building data products and you're actually having organizations that are extracting value from data, there is a need to have an embedding capability and delivery that is connected and agile, connected in an agile way with the domain itself. And this is where the concept of a data mesh is coming out. So, this talk is not going to delve into the concept of a data mesh, but it will kind of like reference to it of why there is this need of this canonical stack, right? And these canonical stacks, there is a need for just multiple different tools at different stages of the machine learning lifecycle that actually branch out. So now you have a broad range of heterogeneous systems that you have to deal with. And with that comes some challenges of metadata at scale, right? When you're dealing with organizations that are at web scale, you have complex challenges in complexity and extensibility. So this was actually from a talk from the team that authored Data Hub, which is a large-scale data management system that came out of LinkedIn. And these are some of the challenges that were highlighted of metadata at scale. So there is complexity and extensibility challenges. The fact that there is this sort of like decentralization, democratization of data products, the need for best-of-breed tooling, the need for integrating with SaaS platforms, the integration with open source platforms, the need for the different schemas of data. In some cases, the benefits of like loosely typed so that you can like dump any sort of like data shapes or data schemas, but also strongly typed in order to actually consume and get value from the data. The challenge of schema evolution as your data changes and evolves. The challenge of extending for particular use cases. There are challenges with scale and heterogeneity, right? The relations of data, whether it is like graph data or relational. Whenever you deal with massive scale and you have like graph data, you perhaps are dealing with very complex queries that may involve hundreds of millions of nodes or vertices, which may no longer fit in a single architecture. You may also have bottlenecks with database types, whether it is like transactional or NoSQL or key value, better than NoSQL, queries, and perhaps even like the need for full text search, right? Like a la Elastic search type queries. Then there is reliability, right? The requirements that you have of like system reliability at web scale, but also remembering that data reliability is different to system reliability, right? And there are challenges that are very complex that actually differ to that of the system reliability ones. There are challenges of real-time synchronization across your different broad range of systems, zero downtime requirements when performing like data migrations, full audit trails, etc., etc. And what then this implies is that when it comes to be able to deal with your data through your metadata, even dealing with the metadata itself, your metadata may be as complex and as large as your big data itself, right? And then that begs the question of like, when you perhaps look at a system like Data Hub, your first thought, or my first thought was, well, why does a metadata management system have to have literally all the databases and have to have such a complex architecture? In this case, basically, if you look at the Data Hub architecture, having like Elasticsearch, Neo4j, MySQL, some metadata crawlers that, connecting to Kafka for streaming of your metadata, etc., etc. And that is because of that challenge that now when we're dealing with metadata, it's not just metadata of a particular set of models, but it's organizational wide and with different modalities, right? It's like if you want to perform rich text search, or you want to perform high throughput queries, or whether you want to perform relational type queries, this actually needs some thinking of how it can be tackled. Now, if we extrapolate the challenges that you have in data metadata, because so far we have been talking specifically about the traditional view of metadata, right? So data metadata, which is now being referred to as data ops. So in this case, the reasons why you would want metadata of your data is for things like data discovery, right? It's like, what are the tables that I have available that I can consume to get value from? What is my schemas that are available so I know how to deal with them? What is the versions of those schemas? What is the ownership of the data? What is the taxonomies across my organization of that data? What is the lineage of the data? But once you're diving into ML, the current state of how we have seen machine learning metadata is it has been one-to-one mappings with how we see data, right? So that is basically what we have seen so far, like the concept of a model card, right? The information about a machine learning model, what is the modality, what is the data that it was used, what are an artifact itself that was created for my machine learning model, the different versions of artifacts, the model dependencies, the risks of that model. But now the purpose of this talk is to basically challenge this current perspective and basically say how it is not enough. And we actually have to go beyond in order to understand and really be able to tackle metadata for production machine learning. And in this case, when you're dealing with operationalization of machine learning, you have to deal with the intersection of data ops and microservice challenges, right? Or systems, web scale systems challenges. Because now you're dealing with machine learning service discovery, inference data schemas, model data schemas, right? It's like, how do I consume a particular model? If we think at models as perhaps like, you could think of it as a database function or a database transformation where you can send a particular data input and then you get an output. You want to understand, like, well, what is my available set of models that I can consume? But now you have to think about it not just as a particular machine learning model, and not only just as potentially a machine learning pipeline, but as a machine learning system, right? And we will dive into what that means. The system risks, the system ownership, the system value that we can extract from our operational environments. Now, let's actually ask the question of what we're talking about now as machine learning systems and not machine learning models. So let's take a look at the experimentation area, which is the more traditional kind of production machine learning area that we have seen. This is where we perform things like hyperparameter tuning, distributed training, evaluation of models, or just with different like ETL frameworks, etc., to produce basically artifacts, machine learning artifacts from training data. Now we want to actually consume those artifacts. We do that by making those artifacts available for inference, right? That could be done with direct kind of manual productionization or through continuous delivery mechanisms, which allow us to make those artifacts consumable in a real-time or batch manner. But that doesn't stop there, right? Because now that we have a operationalized machine learning model, we have a risk that we have to manage. So now we have to make sure that we are managing that risk with the respective observability, the respective, even also advanced monitoring, which can involve even further advanced monitoring components like drift detection, outlier detection, explainability models, etc., etc. And now every single thing that is going through our production environment, a production machine learning system, we have to make sure that all of that is actually captured so that we can have auditability, reproducibility of the inputs and outputs together with the particular models, the versions of the models. And now that data that we have in our inference environment, that data that we don't have is not training data, because in many cases, we're not going to have, in supervised learning, having the labels. In order for us to actually then bring it back into our data ops world, we may need to have different transformations. We may need to have different information about the data itself so that we can actually bring value back into the data ops world. Now, let's ask the question, what is the metadata that is involved here in order to achieve that? That's the question of this talk. And why is it different? So, in terms of looking at that, we first want to see, okay, what are the limits of model metadata in how we see it today? And the way that I want to ask this question is, what are the limits of the concept of model artifacts, right? Because that's the closest that we currently think of. This is a generalization, but let's just think about model artifacts that say, this is how to manage metadata. Why is that not enough? So let's see what are the resources that you have. First, let's say that we have a bunch of data instances from dataset A, right? So we have data instance A1 all the way to data instance AN, right? This could be like a row. This could be like a data instance, right? And we basically train first a machine learning model A, a machine learning artifact model A, with this subset of data instances, right? So now we have a model artifact, A1. And we do the same with different subsets of our data set, creating different experiments, right? Creating different artifacts. Now, this is the challenge, right? When we actually want to operationalize those machine learning models, we don't just operationalize that model and that's where it finishes, right? Because the way that we do it, right, whether we want to operationalize model A1, A2, AM, or model artifact B1, B2, BN, when we actually operationalize them in, let's say, an operational environment, we can actually deploy, let's say, or operationalize model A artifact AM into environment CX, but also into environment CY. So what do we have now? We now have a one-to-many relationship with our models, right? But what, even if we take it to the next level, what if we actually have a pipeline that actually uses this artifact AM as a preprocessor, and then another artifact as a post-processor? So now we basically have a many-to-many relationship between our model and our use of our model, right? Our blueprint and our instantiation, right? So we have a many-to-many relationship that has to be considered when it comes to metadata, right? We no longer can say, okay, this artifact has these properties and that's it, right? It's like now we have an operational instantiation of this model, and we want to know if something goes wrong, where did this come from? What was the configuration? And where else perhaps it's being used? So I mean, these are just some a subset of things, but those are kind of like an initial set of challenges that we want to first tackle. So how do we tackle these deploy model relationships? So the way that we have initially tackled it is by ensuring that the operational component is able to do two things. The first one, it's able to actually be sort of deployed with any arbitrary metadata. So for example, if you have a model that was trained with DVC or with MLflow or with Pachyderm or whatever, you would be able to pass a set of like tags that provide you with that unique identifier, the DVC identifier or the MLflow identifier that would actually be embedded as part of this, together with any operational metadata that is part of the model itself. Now, the second part is that this model metadata, sorry, this service metadata or machine learning service metadata can also be consumed by any external systems that want to actually push that metadata upstream, right? That means that you would be able to ask the question of what are the digital assets that I have available, that I have operationalized, that I can consume, right? This being able to actually perform the key value of metadata itself, which is enrichment so that I can have the data that I need. But more importantly, discoverability is what do I have out there, as well as lineage is what have I had out there, together with the reproducibility. Now, the key thing is that if we go back to the initial premise, which is that we're now living in a best of breed environment, right? An environment where we're going to bring in the best tool for the craft. We have to make sure that each of these systems are taking these principles by design and ensuring that they are providing this metadata in a way that allows for interoperability. So what we have done with in this case, our system, which is actually this production deployment machine learning system to have kind of like pipelines running in Kubernetes called Seldon Core, is basically we've said, look, we will be able to provide the metadata that is existing in this tool for consumption upstream. So external metadata stores can ask the question of, hey, what is running inside? And then can actually build those taxonomies on top of that, right? So that's a key thing. So that was the first challenge, right? Like data relationships. Now let's dive into the second challenge that we talked about. When we're capturing the data, right, the inference data, not our like static data, however we want to call it, data ops data, the inference data, when we're capturing it, it may have a different shape or schema. How do we make sure that all of this data is still consumable, is still fit for use, and it's not just like binaries that are flying around? And why is this a problem? Well, this is a problem that we want to address because whenever we are actually productionizing machine learning models, we're no longer productionizing just ML models. We're productionizing ML systems. Rarely now you see organizations that are tackling a particular, large challenge that actually just involves, an iris classifier. It never has involved an iris classifier, but like a simple machine learning model. If you look at a lot of the production grade, large scale machine learning systems, in this case, for example, this is the Facebook search architecture. This has actually multiple components, right? It has online components, offline components. In this case, basically, you have the offline component that creates the document embeddings, right? It actually processes kind of like an embedding space that is quantized, that then it's available so that whenever you actually perform a search, you have kind of like query processing, then you have the retrieval that uses that embedding and the ranking itself so that you get your results, right? So this is a complex machine learning system. It's not just a model. So with that machine learning system, we have different components that have to interact with each other. And the challenge that we see here is that whenever you deploy a machine learning model, at least previously, each of these machine learning services had a different schema, a different input schema and output schema, how you communicate with that, how do you perform inference. So one of them, the TensorFlow protocol, it used to be in one shape. The MLflow protocol was another shape. The Seldon protocol was another shape. The Kserve protocol was another shape. And the PyTorch protocol was a binary, right? You send a binary. Now it's no longer, because we actually have a great collaboration that has been cross-industry. which is basically the creation of what we now refer to as the Open Inference Protocol. So the Open Inference Protocol is basically a protocol that has been adopted by several of very kind of like largely adopted machine learning servers that are currently used in production to deploy machine learning models, such as like TorchServe, Kserve, Seldon Core, NVIDIA Triton, and even MLflow, because it uses ML Server, or there's an ML Server runtime that you can adopt. And basically, the reason why this is great is because now that means that the data in flight is standardized, right? And this is a great thing, because now the data in flight can be consumed in a much more standardized way, and it can actually be processed in a way that can be much more meaningful for production machine learning use cases, and more specifically for interoperability when creating machine learning systems, right, with multiple different stages. Now, it doesn't stop there, right? Because the first step is to basically say, hey, what are the baseline requirements to make sure that we have an aligned schema, right? So, and this schema is great, right? Because it provides a standardized set of endpoints for not just the shape of the inputs and outputs, but also the functionality. It has a multi-model serving API for management at the back end. It has capabilities for multi-version support for models. It has health endpoints, and it has metadata endpoints. So it not only standardizes the data in flight, it also standardizes the functionality that it should provide at the base minimum, which is great. But the second thing is, once we have the data over here in our deployment, how do we consume it back into our experimentation, or even further into our data labeling, right? And that is basically with what we actually have been able to tackle, which is, now that we have a standardized definition of the data in flight, we can now come up with a schema that describes that data, right? And the actual schema basically allows you to specify, is the data that is sent to the model a real data instance? Is it categorical? What is the categories? Is it a probability base? Is it a one-hot vector? Is it text? Is it a tensor? And that has actually been released to ensure that you can extrapolate for your pipeline. So it's like, if you have this shape of inputs for each of the steps, now you can understand what are your expected pipeline inputs and pipeline outputs, as well as complex pipeline inputs and outputs, and even your complex machine learning system inputs and outputs at the different stages. And we have been able to release this under the name of the Open Inference Schema, which is basically another standard that actually builds on the Open Inference API that allows you to be able to not just have a standardized way of communicating between servers, but also being able to actually convert this data into machine-readable formats, which I think is great. And this is basically self-explanatory. You describe what the input shapes are, and that allows you to be able to consume the data that is at flight. Now, finally, just to kind of wrap up, there's a very important call to action, right? Is that, yes, it's great that these things have been created, but now what we would want is to make sure that there's further adoption of these standards, and there's further contribution to these standards, right? It doesn't end here. We want to make sure that, whilst we're focusing specifically into the productionization, because that's the projects that we maintain, we need these initiatives to be similar for all the other stages of the machine learning lifecycle. So any practitioners that are involved in other stages, the call to action is to also get involved and driving forward some of those things with the various organizations, such as the Linux Foundation, as well as others. So with that, today we covered metadata systems for end-to-end data and machine learning platforms. I hope you enjoyed the session. Once again, as a reminder, you can find the slides on bit.ly/metaup. And with that, I hope you enjoy the rest of the conference. And I'll pause there. So thank you very much.